Good morning. Today's lecture is chapter 4B. So we took chapter 4A, and now we are going to take chapter 4B, combined footings. Let's just remember, we started with chapter 2, shallow foundations. We studied everything about shallow foundation, the concept of shallow foundations. Then in chapter 4 we took isolated footings as one type of shallow foundations. We studied isolated footing subjected to normal force and moment in one direction, two direction, changing, constant, everything. So now we studied up till chapter 4 isolated footing. Then we said that we need to study other types. The first thing in the other types was the strip footing, which we said that it is a footing with more than one column or maybe a long wall. Now we want to study combined footings. What is or what are combined footings? Combined footings, let's just go to this slide. This is the plan of an isolated footing. This is the column, this is the reinforced concrete, this is the plain concrete, and this is a cross section in the column. In this arrangement, suppose we have two columns very close to each other, and when I come to draw them, I found that there is an overlap between both footings. I don't consider the overlap in the plain concrete as an overlap. The start of the overlap is the overlap in the reinforced concrete. So if the overlap is just the overlap in the plain concrete, we can ignore this and it will be okay. But when the overlap is in the RC, maybe the drawing does not just show an overlap in the plain concrete, but no, consider the overlap to be very accurate. Consider the overlap to be also in the reinforced concrete. So in this case, if I have an overlap in the reinforced concrete, I cannot construct something like this. So what I need to do is to construct, to design one footing carrying both columns. Here, by the way, in the cross section, it is clear that the overlap is also in the reinforced concrete. Maybe here it needs minor modification to show that the overlap is also in the reinforced concrete. So now we understand we need to design a footing carrying two columns close to each other. So, as we said in the previous lecture for strip footing, we don't need to discuss anything or say anything. We just go to an example because it is an application for an isolated footing. What we usually do, what are the steps that we are going to follow? Number one, if I have something like this, here is let's go to the drawing. Where is the drawing? This is my drawing. If I have something like this, I need first, before going to designing combined footing, I need to prove to myself and to the person who is reviewing my design that there is an overlap. How can I check this? By designing each footing alone. So this is the first thing. Check isolated footings. I will check isolated footings. I will take the first column, get the dimension, length and breadth. I'm not going to design the thickness. I'm just designing the length and the breadth of the footing, the plan of the footing. And I get the plan of the other footing because maybe the columns are not equally loaded. They may be different in loads, so they will be different in dimensions also. And then I check, is there a possibility that I may change the dimensions of the footing so that they won't touch each other? Maybe I would increase the width in the perpendicular direction. Here, if I suppose I have this, if I increase this width and decrease this length, if it is possible to do this and I still have isolated footing, I would do it. But if I can't and I find that they are overlapping each other, then I will have to do a combined footing. So the first thing is check isolated footings for both. If they are not adequate and they overlap, then I'm going to use a combined footing. The area of the combined footing is calculated to guarantee what? First, it should guarantee that it is safe in terms of bearing capacity, similar to any footing, but based on the load of both columns. So I will take the load of both columns, get a new area that would guarantee a safe bearing capacity on soil. We ensure that the two columns are within the inside of the base area. Of course, if I have this column and this column, and I design a footing, suppose that my footing, that the footing I designed is something like this. It ended here. So this part is not with me. Then it means that part of the column is outside. I cannot do this. So I need to guarantee that both columns are included inside my new dimensions. Ensure that the resultant forces of the two columns are concentric or consistent with the center of the base or with the footing. If I have, let's just go first to the case of an isolated footing with one column. In case of isolated footing with one column, where is the CG of the column? Here. This is the CG of the column. Where is the CG of the reinforced concrete footing? It is also the same point. So it came without saying that the center of the footing should be the same as the center of the column. Otherwise, if I don't have this, what will happen? There will be additional moment on the footing. Suppose that I shifted this column in this direction. What will happen? If I shift the column in this direction, it means that this will still be the center line of the footing, but the center line of the column will be here. It will be shifted a distance. It means that there is an eccentricity. This eccentricity will result in a moment in this direction. So I have always to check that I have zero eccentricity. The CG of the column is the same as the CG of the footing. The same for this case. If I have these two columns, it means that the CG of these two columns should be the same CG of the footing. Where is the CG of two bodies not touching each other? The CG will be outside. It is the resultant. It depends if this column has the same load as this column, then the CG of both columns or the resultant of both columns is just in the mid area, in the mid distance between them. But if this is bigger, if this column is bigger, then in this case my CG will be shifted to the bigger load. We'll see this in our design, but it means that when I come to design a combined footing, then I have to check the CG of the loads of those two columns. Where is the CG? Suppose the CG is here at this point. Then in this case, this point should be the CG of my footing. In this case, my footing should be shifted a little bit this direction so that its CG would be concentric with the CG of both columns. This is exactly what we are going to do now. And in this case, we are going to design the combined footing. What are the steps of my design? Similar to the steps of the design of one isolated footing, because I'm going to design this footing based on the resultant of both forces, the summation of both forces. So I will check, so I now know the dimensions, then I need to check the depth. Once I check the depth, I check shear, and then I check punching, and when I find that the depth is safe in shear and punching, then I will get the area steel of the footing. Let's go to an example directly. I have two columns. The first column is carrying 1,500 kilonewton. The second is carrying 1,200 kilonewton. From what I've just said, it means that the CG of both columns is somehow in between, but I should expect it to be closer to this column because this column is carrying a heavier load. So I expect that my CG will be somewhere in this direction, at this location. What are the givens? The given are Q allowable for soil is 150 kilonewton per meter square. The thickness of the plain concrete is 30 centimeter. FCU of concrete is 30. F yield is 400, similar to the numbers we usually use in our examples. So we start putting our answer. The first thing, I repeat the given and calculate what I need from the given. The column dimensions, it is given 400 by 700 because it is written here on the, it may not be given here, but it is given on the drawing. It is 40 by 70 for both columns. So the column dimensions 40 by 70 and 70 by 40 because the only difference is in the orientation of the column. The loads, the first column carries 500. This is the working load, and the other 1,500, and here 1,200. What is the ultimate? Multiply these by 1.5. So these are the ultimate loads that I will need when I come to design the thickness and the amount of steel. Bearing capacity of soil given 150, F yield and FCU are also given. So these are the givens. First thing, check isolated footing. How I'm going to check isolated footing? Divide the working load of the first column by the bearing capacity of the soil, and divide the second load of the working load of the second column by the bearing capacity of the soil. So this is one area, this is the second area. Get the corresponding dimensions of both, and we said that we usually take the difference between the length and breadth of the isolated footing. It is better to be equal to the difference between the length and breadth of the column. So I have a column 40 by 70, so the difference is 30 centimeter. So I need dimensions where the difference is 30 centimeters. Similar to any previous design, I will get the B and the L for the PC and the RC of both columns. I will draw both on my drawing. I find here that there is an overlap. Of course, if the overlap is just 25 centimeters, maybe it would be better in actual case that I would reduce this direction and increase the other direction. I will still get the same area, but there will be no overlap between both footings. It is possible, but for the example, I am going to design this as a combined footing. Why do I prefer two isolated footings than one combined footing? Because it will be cheaper. Why is it cheaper? Just a reminder, this is an isolated footing. If you remember, in isolated footings, where is my steel? I only use lower steel. I don't have upper steel. But in case of a combined footing, if I replace this with one combined footing, it will be like a beam with two columns resting on the soil. There will be negative moment, positive moment, so I will have to put upper and lower steel, so the price will be much higher. So this is a rule of thumb. When I have a way to replace a combined footing with two isolated, go ahead and do this. So now I need to design a combined footing. What should I do? As we said, I need the CG of the loads to coincide with the CG of the footing. So I need to get the CG of the loads. I have one load here, it is 1,500, and here it is 1,200. What is the value of the resultant? The total of the resultant, of course, it is the sum of both loads. So this is 1,500 and here is 1,200. The resultant is 2,700. This is just summation. But what I need to prove, where is the location of this resultant? To get this summation, or this resultant, then the easiest thing is to say that moment at this point equal to 0, or moment at this point equal to 0. Suppose I say moment at this point equal to 0. It means that this moment multiplied by this arm is equal to the resultant, but I will put now the resultant in the opposite direction, because it is not the resultant that I'm using, it is the reaction of the soil to both columns. So the reaction of the soil will be in the opposite direction. So 1,500 multiplied by 2.3 should be equal to 2,700 multiplied by this distance. So it's just a normal equation, one unknown. I will get this to be 1.28. So now I know that this distance is 1.28. So now I know where is the CG. This is the location. I will go back here. If I go back here to this, it means that if I go from this distance 1.28, so from here, just from here to there, this distance should be 1.28. So this distance should be 1.28. Now we continue. We knew that it is 1.28, my distance. Then I need to calculate the area of the footing. How to calculate the area of the footing? Of course, the area of the footing is the area that will be carrying the resultant of these two forces. So I now have a new force. This is my new force. My new force is the red arrow replaces both blue arrows. So 2,700. If I divide it by the bearing capacity of the soil, it will give me the area of the footing that I need. So this is what I'm going to do. 2,700. Of course, I'm using the working load, not the ultimate, because I am dealing with the bearing capacity of the soil. So it is the code of the soil that deals with the working loads. So 2,700 divided by 150, 18. 18, it should be here meter squared, because 18 meters squared is the area of the required new footing, new combined footing. So this area should be equal to what? We'll just see here. Let's go to this. Imagine that this, we said that this is the resultant, and this is the place where I need my, when I need the CG of the footing to be. So the distance from here to there is just the half of the total footing. So now I know where is the half. Let's sum up the distances. From here to there, it is 1.28, what I have just calculated. From here to there, this is half the width of the column. I know it. From here to there, this is unknown for me, but as it is given by common practice, we take it something between 0.5 meter to 1 meter. If I take it something between 1 meter and 0.5 meter, it will be okay for me. And what about this distance? This distance is the protrusion of the plain concrete out of the reinforced concrete. What is the protrusion? It is equal to the thickness of the plain concrete. It is given here that the thickness is 30 centimeter. So I know that this is 30 centimeter. So this number is the only unknown I don't know. And we said that I'm going to take it something between 50 centimeter and 100 centimeter. Then I would take it something, start with 50, start with the small one. But if I take it 50, I will not get a round number for the total of the footing. My footing should be a round number. It should be a multiplication of 10 centimeters. So in this case, if I take it 0.52 meter, 52 centimeters, the summation will be okay. Here, if you look, I multiply by 2 because I'm dealing with half only of the footing. So half of the footing is 1.28 plus 0.2, which is the thickness of the column, half the thickness of the column, 0.52, which is the dimension that I have assumed, 0.3 is the protrusion. I end up having a footing where the L is 4.6. Now I know the L, I need to know the B. And I know the total area. The total area is 18. 18 divided by 4.6, it is 3.95. So now I know the dimension of the plain concrete, L and B, and I can calculate the dimension of the RC. Let's see this in a plan. Yes, this is a bigger plan. This is my new plan. I calculated the length from here to there, multiplied it by 2 to get the full length, and once I get the full length and I put it on my plan, I have to check this cantilever. I assume this cantilever to be 0.52 meters. The other cantilever should be more or less equal. If suppose that I assume this to be 0.52 and then I checked here, I found that this is 100. No, here my design is not optimum. Of course it will be safe and I will make it safe, but to be optimum design, if this is 0.52, this should be very close to 0.52. So here it is 0.63. Okay, difference is just 11 centimeters. This is okay. But suppose that it is not 0.63, it is 0.93. So it is bigger. How to reduce this? Increase this. If I just, instead of, I was going to assume this from 0.5 to 1 meter, and I took it 0.52, take it 0.62, and so on. Assume this 0.62 and check this. If both are within the same range, then it is okay. So this is my dimension, and I knew the other dimension here. The other dimension is given here. B, it is 3.95. So this is the B of the plain concrete. So I also know the plain concrete. So from here to there, this is the B of the plain concrete. From here to there, this is the L of the plain concrete. And inside is my RC, that is 0.3 meter all around inside my plain concrete. So now I have all the dimensions I need, and I checked it, and here it is okay. The dimension is reasonable with the other. This cantilever is okay with this cantilever, and the cantilevers here in the other direction are also more or less within range. So my footing will be economic. Now I go to the design. Now I have, imagine now, I have this one footing is like a beam. This one footing, I have here, you remember my column loads here, just a moment. Where is my loads? I will, yes, here. These blue arrows represent the original loads, and this was the resultant. This red arrow is the resultant of both. Now I replaced the resultant with these small arrows because they represent the reaction of the soil. This is the actual loads coming on the footing, and this is the actual reaction coming from the soil. Now I have a beam similar to a beam or a plate that have two loads on top and soil reaction from the bottom. You can draw the normal force, the shearing force for this beam and the bending moment for this beam. This is what we need in our design. So I will just get what is the value of this of these loads. But why I'm going to calculate this reaction? I'm going to calculate this reaction to calculate the bending moment and the shear. What I'm going to use the bending moment and the shear in? I'm going to use them in the design of the thickness of the footing. First, in the design, in calculating the bending moments. These bending moments will be used in calculating the thickness of the footing and the amount of reinforcement. This I use the code for reinforced concrete. In this case, I need the ultimate load. So now I take the resultant of both columns, multiply it by 1.5 to get the ultimate, then divide them by 4. 4 is the L of the plain concrete, of the RC, the L of the RC, because now I'm going to design the RC. I don't deal with the plain concrete. I'm going to design the RC. So now I know that the L, which is this dimension from here to there, it is 2 meters from here and 2 meters from there, so it is 4 meters. So I divide the total load of both columns by this dimension. I get the load per meter run here in this direction. This load per meter run is the reaction coming from the plain concrete on the reinforced concrete. So now this is my Q ultimate. I'm going to use this Q ultimate in my design. Similar to any previous case, I need to calculate where is the maximum moment. In this case, in my footing here, if you remember, it is very easy to detect where is the maximum moment. The maximum moment for this cantilever from all direction, it is at the edge of the column. At the edge of the column, I have the maximum moment. But in my case here, where is the maximum moment? I don't know. There is an old rule in structures. It tells you that the maximum moment is at the location of the point of zero shear. This is a structural rule of thumb. This is the point of zero shear. If I manage to calculate this point, then this point will be exactly the point of the maximum moment. And here there is a cantilever. Here there is another cantilever. Here I can calculate the moment here and the moment there of the cantilever. But what I don't know is the maximum moment in between these two, in this span, because this beam is actually a beam that is resting on this column and resting on this column, and the load is the reaction coming from the soil. So it is as if you have an inverted beam. This is the support of the beam, here the support of the beam, this is the load, and the load is here, and I need to calculate, to draw the bending moment. What will be the shape of the bending moment? Just, it is there, but I want to draw it here. I will have a bending moment like this, something like this. This is the moment of the cantilever. This is the other moment of the cantilever. Of course, here the moment is less than there because here the distance is less. And I now have here another bending moment here like this. And this is the point of the maximum moment. You will see this here. This is exactly what I just drew. This is the bending moment at the column here, at the cantilever here, and this is the bending moment at the cantilever here, and this is the bending moment at the inside the span, which coincides with the point of zero shear. So now I can. I have the shear and I have the bending moment. Actually, I have here three bending moments. One at the first cantilever, one at the second cantilever, and one in between the two columns. As you know, we always try to have some cost savings. Instead of calculating, as I said here, instead of calculating the bending moment at the CG of the column, and this is really a hypothetical case, why not calculate the bending moment just at the edge of the column? Because here I have a column. Of course, the bending moment in the middle of the column, I don't care for it. I care for the bending moment just after the column. So I'm going to calculate the bending moment at this point. This point is the edge of the column. Here is the edge of the column, and here is the other edge of the column. So I will calculate the maximum here at this location, and I will calculate the other here at this location. But of course, what I need more is the bigger. So this is the bigger one, because this is a longer cantilever. So I'm going to calculate the bending moment here. So the bending moment here is bigger than the bending moment there. And I have another moment in the opposite direction. If this is my footing, and this is a moment, and this is a moment, if I'm going to put my reinforcement, then I will put reinforcement like this, This is one reinforcement like this at the bottom, and this will carry the bending moment here and the bending moment there. But for the upper one, I'm going to put another steel reinforcement like this. So this upper reinforcement will be designed based on this moment, and this lower reinforcement will be designed on the maximum of both cantilevers. So this is what I should do. But before I proceed, as we said, we need to check shear and punching. Why do we need to check shear and punching? Because if we do not check shear and punching, maybe the footing is unsafe, and the only thing I can do if the footing is unsafe is to increase the depth, and at this case the calculated amount of reinforcement will be reduced. So it is better to wait, not to design the amount of steel except after checking shear and punching. So usually I'm going to check shear similar to per column. I will take the bigger column, check shear around this bigger column. If it is safe, then okay. Unsafe, I will increase. Then check punching around the bigger column. If it is safe, it is okay. If it is unsafe, similar to what we have done in the case of isolated footings. If it is unsafe, we are going to increase. This is the check of punching here, given in details. And based on my check of shear and check of punching, both are okay or not okay, and I'm going to change the depth. Then now I'm ready to design the steel. But before designing the steel, remember that I was speaking here about which direction. When I said that I'm going to put my steel here and there, this is the longer steel. But what about the steel in the transverse direction, perpendicular? Here, if this is my plan, I'm going to put steel here. This is lower steel in this. Just a moment, I'm sorry. I'm going to draw it a little bit better. If I have here, this is my first bar, reinforcing bar here. This is the lower one, and I have an upper one here like this. Of course, it is repeated every, say, 20 centimeters and so on. These are my reinforcement in this long direction. What about the other direction? I have here another direction. I need to put a reinforcing steel here. As you see, we said here I have bottom and upper reinforcement. Not like in case of isolated footing, I only have bottom reinforcement in isolated footing. But in this case, I have lower reinforcement, upper reinforcement, and in the transverse direction also I will have upper and lower reinforcement. So it is very expensive compared to the other one. So now I need to calculate this steel. So this steel needs a moment in this transverse direction. I calculated the moment in this longitudinal direction. Now I need to calculate the moment in this transverse direction to get the steel here. So this is exactly what I'm going to do now. This is the transverse direction. I here took a dotted line at a distance of D. D is the depth of the footing. I take a distance D here and D there, and I say that this area will be concerned, this area only, will be concerned with carrying the transverse moment in this direction. But what about here and there? These are will not be affected, and I'm going to use minimum steel. So here I'm going to use minimum steel, here I'm going to use minimum steel, here minimum steel, but from here to there, this will be the transverse moment based on this column, and here this will be the transverse moment based on this column. So actually when you come to the plan, you will find that you have three categories of reinforcement. One here, this is minimum, this is also minimum, this is also minimum. Here, this is maximum because it is the transverse direction of the bigger load, and here it is something intermediate because it is the transverse direction of the lower load, and so on. So the same. So in this case, I will assume that I have, as if I'm having two footings, one B1 and one B2. I will take the load of this footing divided by this area and get the corresponding moment as if this is a normal cantilever. So I'm going to divide the load by this load by this area, and this load by this area, get the bending moment based on a cantilever, WL squared divided by 2, and I will get the moment. Based on this moment, I will design the steel. Of course, here I'm going to use also the ultimate load, not the allowable load, because I'm still designing the steel. So for the transverse direction, I will design both small imaginary footings, and so on. I'm going to calculate the amount of steel that is required for all directions. So, but in all directions, I will have top steel and bottom steel, and I also need to calculate the minimum steel based on the thickness of the footing. So this will be my minimum steel. If I go to the plan, let's have a bigger plan, something like this one is okay. This is the bigger plan. I will this is cross section. Maybe and this is the plan. So now I have, this is the plan. This is the steel, the longer steel. Here the longer steel have a different shape. I will discuss it later. But this is the longer steel. This is the lower, and there should be and this is the upper, the dotted one. This dotted line is the upper steel. And here, this is the lower steel in case of the transverse direction, and this is the dotted one is for the upper steel. So I have upper and lower steels in both directions. Just to tell you what do I mean by the shape of the reinforcement, I will use this plane. I can put my reinforcement as a U-shaped like this. This is my U-shaped steel. I can do this. And this U-shaped will be used all over this length or this breadth. From here to there, I will use this shape. You know that we always need to make some cost reductions. So to make some cost reductions, instead of using this bar like this, and as you see, I don't really need this big leg here and there. So what can I do? In case I find that the distance between this bar and the one next to it are very close, it is less than 20 centimeters, maybe it is in the range of 10 centimeters. So I can just use one bar like this and remove this portion and use the one next to it to be like this, the opposite. So one with a leg here and one with a leg in the other direction. So instead of using all of my amount of steel using a U bar, I'm going just to use it as an L bar, and 50% of the L bar and 50% of the same L bar, but in the opposite direction for the leg. So this is what we do in case we have very high amount of steel. So if I have very high amount of steel, one will be like this and the one next to it will be like this. This is just for cost saving. Suppose you don't do this, it's okay, but you are not saving for your client or for the owner. This is only, these are shapes taken from the Egyptian code for the reinforcement, and what is the relation between the column and the reinforcement of the column and the reinforcement of the footing. And here it is very clear to you. You see these small dotted steel rebars. These are the rebars in the transverse direction. If you see here, they are here very close to each other, but here they are away from each other. Why? Because this is the portion where I said that I'm going to use minimum steel. You remember that based on this, we said that at this location, we are going to use minimum steel. Here minimum steel, here minimum steel, but here the amount of steel will be the exact amount that I need, and here the exact amount that I'm going to need. So you will find that here there is a concentration for the steel, here concentration for the steel, here is minimum steel. This is the first thing you have to take into consideration. The second thing is that I have upper reinforcement in both directions, and this is the main reason for the increase of the cost of the combined footing. But actually it solves a lot of problem, so I need to know it, and it should be one of the types that I know by heart for in the design before I start working in the field. This ends up our combined footing. So now we know the combined footing, the strip footing, and the original isolated footing. All of them are part of my shallow foundations. Thank you, and see you next lecture.